Good morning, B Block. All right, today we are going to look at limits of transcendental functions. Transcendental functions are essentially functions that transcend the polynomial function. So we're talking about our exponential, our logarithmic, sine and cosine, like all of those functions that are a little bit more than just those polynomial functions that we're used to. So we are going to start with just we're going to see different types of these functions. So one thing that you'll see are basic substitution. So just as a reminder, when we're evaluating limits, sometimes we have a continuous function. And so when that happens, we can simply substitute in. So let's say we have the limit as x approaches 0 of e to the x times cosine x. Before I try to do anything fancy or try to think crazy thoughts, I'm going to go ahead and just look and say, can I put 0 in for x? So I know that e to the 0 would be 1, and I know cosine of 0 is also 1. Make these look more like ones. And so 1 times 1 is 1, and I'm good. And so don't look at one of these and immediately think, oh man, this is going to be rough, because it could be pretty straightforward in just a substitution. What about this? All right, so now we have the limit as x goes to pi over 2 of e to the x times sine of x. So although it looks funny, we can put pi over 2 in for x in e to the x. We just get e to the pi over 2, so that's fine. And then we know that sine of pi over 2 also equals 1, and so we just get e to the pi over 2. So again, all of these situations, both of these situations have resulted in us being able to just substitute in for an expression. Last one, let's do the limit as x approaches 4 of the natural log of x subtract 3 multiplied by, let's do e to the x plus 1. All right, again, it looks super, super complicated. You look at it and you're like, there's no way I can do this. However, we go ahead and we just substitute in. We have the natural log of 4 subtract 3 times e to the 5th. So if I'm analyzing this further, I have the natural log of 1 times e to the 5th. What's the natural log of 1? So e to the what power gives me 1? We get 0. 0 times e to the 5th is just 0. And so if we look at any of these graphically, we would see that we could actually just follow them along on Desmos, because these are continuous functions. What I'm evaluating is also what my function would equal at that x value. All right, now we're going to look at things that we need to think about more conceptually, and these are the limits at positive and the limits going to positive and negative infinity. So let's start with something a little bit more basic. Let's say we have the limit as x approaches infinity of just e to the x over x. All right. This is very, very similar to those rational functions when we had like x to the 5th in the numerator and x to the 4th in the denominator, or we had x squared in the numerator and x to the 3rd in the denominator. And we had to think about more about, is my numerator or my denominator getting larger faster? And that's what we cared about every single time. And that's what we care about this time. And so I'm looking at this e to the x. And if I think about these two functions for a minute, e to the x looks like this, right? just y equals x is just a straight, it's just a straight line. It has a constant rate of change, whereas e to the x has an increasing rate of change that's not constant. So at each interval, that rate of change is increasing, whereas my rate of change of a linear function is just constant. It's going to be the same up and over like a set of stairs. My exponential is following more of like a really steep hill, and as we get closer and closer to the top of that hill, it's getting steeper and steeper and steeper. And so since my numerator, this e to the x, so you can't see that, this e to the x is getting larger at a faster rate, what we have to do is, this is getting larger, where are we? This guy right here is getting larger at such a faster rate that this limit's actually going to go to infinity. Because I have an insanely large number on top, and I have a big number in the denominator. It's just not as large as my numerator. So that one we tend to be like cool with, but now let's take a look at something like this. So now we have x to the fifth. So the limit as x goes to infinity of x to the fifth over 3 to the x. Even though x to the fifth, I could even make this x to the 50th. I could make this x to the 500th. That feels really, really large because I'm multiplying infinity by itself now 50 times. But here's the difference. This 3 to the x, I'm never not multiplying. So although at the beginning, x to the 50th is going to have a steeper rate of change, it's going to get larger faster. By the time we get all the way to infinity, this 3 to the x is going to be significantly larger because x to the 50th is finite, right? I'm multiplying infinity, or I'm multiplying an insanely large number by itself 50 times. Yes, crazy big number. However, this 3 to the x, I'm multiplying 3 by itself forever, and I'm never stopping. And so by the time I get to the end of it, I'm multiplying infinity times 3, infinity times 3 again, infinity times 3 again, infinity times 3 again. So even though this x to the 50th is a very large number, it's not going to win out against a 3 to the x, because these exponentials are just inherently, they grow at a faster rate than our polynomial functions every step of the way. So what I'm going to have now is I'm going to have a large number in the numerator, but an insanely large number in the denominator. So I have, this one will go to 0. I know that feels really weird, and if you graph it, it's going to be really hard to even see where these crisscross. You can see it with like an x to the 5th, an x to the 6th. You'll see that like the exponential and the polynomial is a larger value. It's a larger value, and then all of a sudden you'll see this crossover. But we're talking that we need to get into some crazy big numbers before that's going to happen. All right, let's look at another one. So real quick, the big takeaway from this is that exponentials grow at a faster rate than polynomials. That's kind of the big takeaway there. The other one we need to think about, the limit as x approaches infinity of, let's do the natural log of x squared divided by the natural log of x. All right, so for this guy, we can use our properties of logs to simplify these when we can. So notice this isn't the natural log of x squared over x. It's the natural log of x squared over the natural log of x. So I can't use my quotient property, but I can use my power rule for this numerator. So I'm going to go ahead and rewrite this. I haven't substituted anything in yet, so I have to rewrite my limit. And I'm going to rewrite my numerator as 2 natural log of x all over the natural log of x. Notice now I can cancel out the natural log of x, and I get 2. And if we were to graph these two functions, we would see that we have a horizontal asymptote at 2. Well, at least as x goes to positive infinity, we have that horizontal asymptote. Actually, even as x goes to 0 from the right, we would also have that. All right, last type of problem, and then you should be good for your problem set, but try to reason it out. Again, some of the ones like this you won't be able to put into a calculator as easily, but try to kind of rationalize what's going on. And then put it into Desmos and you can check your work. All right, so let's say we have something like this. And we're letting x go to infinity. So for this one, I'm letting x go to infinity right here. Oh, you guys can probably hear Max waking up. And so I have 20 times e to the negative infinity right here. If I have e to the negative infinity, that means I have really 20 divided by e to the infinity. So I have 20 in my numerator and e to the infinity in my denominator. That's going to go to 0. And so what I'm left with is just 500 divided by 1, which is 500. And we'll talk more about this one, remind me, the next time I see you. This type of function was really, really big during COVID. It's kind of mapping out this, we call it logistical growth, like this. And every time they were talking about flattening the curve, this is what they were talking about. They were trying to figure out how to kind of plateau this curve and go from growing at an exponential rate to growing at a more of a logarithmic. Because notice that this portion of my graph looks exponential, and then I get to this part, and it goes to be logarithmic. All right, I hope this helps. Good luck. Have a lovely weekend. Hope to see a few of you guys at graduation.